talk about upper sums, and for this particular graph, it's going to also be considered LRAM, as you notice up top here. Upper sums and LRAM. For this particular problem, these two are not synonymous. Okay, they are not synonymous. If that is spelled right, you know what I mean. Okay, upper sums. So we're going to specifically look at left rectangles, right? Left rectangle area model or left rectangle approximation method. Any one of those, it doesn't really matter. They kind of all mean the same thing. So what that means is we're going to look at left rectangles. We're going to do 6 rectangles in this particular example, given the graph f of x equals 16 minus x squared. Okay, 6 rectangles, and we're going to look at the area under the curve on the interval from 1 to 4. Okay, so first thing I'm going to do is I'm going to give myself a little bit of a visual by drawing some rectangles in here. Now we can kind of do this a little bit ahead of time here. If we're going from 1 to 4, it's a distance of 3, and if we have 6 rectangles, each one is a half. So I'm going to try to make this as much to scale as possible here. So there is a left rectangle. Put another one in here. Another left. Kind of blocking my diagram out here. I think I'll be able to bring them back here in a minute. I think I have an option to make clear rectangles. Okay, and let's do one more left rectangle. Let me see briefly here. I'm going to pause, see if I can get clear rectangles, and I'll be right back. Okay, we are back, and you got the rectangles are a little clear now, so we can actually see the curve underneath. So this is what I mean by left rectangles. The left side of the rectangle is what's touching the curve. Okay, so the left side of the rectangle is touching the curve. That gives you your LRAM. The fact that I have all this excess area above the curve is what makes this an upper sum. Okay, so when we approximate the area under this curve using these 6 rectangles, our answer is going to be too large for the actual area. All right, so let me fill in these last 2 right here, and we'll figure out how to find the total area. Now, granted, there's 6 rectangles here. We can easily find the area of each rectangle, right? The width is 1/2, and the height, if I plug a 1 in to my function, 16 minus x squared, I get the height of 15, so area is 7.5. Boring, okay, and very monotonous, especially if I say, hey, 12 rectangles, 20 rectangles, 30 rectangles. That's tedious. So we have to refer back to our sigma notation. Okay, we know that the area of a rectangle is base times height. Okay, that is fact. We know that. What we also know, okay, we know that the base, or delta x, right, the horizontal width right here, delta x is equal to 4 minus 1, right? 4 minus 1 divided by 6, because there's 6 rectangles. Okay? That's 3 over 6, which is 1/2. The width of every rectangle is 1/2. I'm going to write base or delta x right there, right? You can use whatever you would like there. Okay, now we got to figure out what the height is. The height. Well, my height here is f of 1. 16 minus 1 squared is 15. My height here, I'm plugging in 1.5, so I get 16 minus 1.5 squared. Here I'm plugging in 2, here I'm plugging in 2.5, 3, 3.5, and I'm not plugging in 4. All right, so I need the numbers x equals 1, 1.5, 2, 2.5, 3, and 3.5. I think it's obvious to see they're changing at a rate of 1/2. So what I'd like to do is the first thing I plug in for LRAM is the last rectangle. So my height is a function, right? We have to plug all these values into f, is a function of 4 minus 1/2, and use whatever letter you want. I like to use I. So think about this. When I is 1, I'm plugging in 4 minus half. I'm plugging in 3.5. Check. When I is 2, I'm plugging in 4 minus 1. 3. When I is 3, I'm plugging in 4 minus 1.5. That's 2.5. So on and so forth until I get to my 6th rectangle. 4 minus 3 is 1. I'm plugging in my last value. So for my purposes in left rectangles, this is rectangle 1, 2, 3, 4, 5, and 6. You'll see with LRAM, I change up a little bit, but I believe it's the easiest way to do this. Your other option here, is you can say your height is f of 1/2 plus 1/2 I. Right? Again, think about it. When I plug in a 1 here, I'm doing a half plus a half. 1. Plug in a 2 for rectangle number 2. I get a half plus 1, which is 1.5. Plug in a 3. Half plus 1.5 is 2. All the way up to the 6th rectangle, I'm plugging in a half plus 3 or 3.5. Okay, in that case, this would be rectangle 1, 2, 3, 4, 5, 6. 6 in one, half a dozen in the other. It makes no difference. Personally, I like dealing with 4s rather than halves, but it's your call. All right, let's get to the nuts and bolts of this problem now. So the overall area is 1/2 base times all of the heights. Okay, that would be the height of triangle 1, height of triangle 2, height of triangle 3. So in other words, height for triangle 1 is f of 3.5. Triangle 2 is f of 3. Dot, 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 all the way down to the height of triangle 6 is f of 1. Okay, that's a little tedious. So what we do is we use our sigma notation rules, and we turn this into a sigma problem. Okay, in sigma, we can write repetitive addition. So my area now, 1/2 is going to multiply by everything, but instead of writing out those 6 rectangles, I'm going to say that sigma goes from 1 to 6, and it's f of 4 minus 1/2 I. Right? These guys are all heights right here, and this is how I defined my height, a function of I. So I can plug that in here, 1/2 times each of the heights, 1 through 6. And now we can use some simplification. We're going to plug in 4 minus 1/2 I. Right, this is f of, so 4 minus 1/2 I gets plugged in here. I have 16 minus 4 minus 1/2 I squared. Right, we just did a straight substitution instead of x. Right, instead of x, I'm plugging in for x. Okay, let me scroll down some more. I'll lose some stuff here, no doubt. A lot of stuff disappearing, but we're going to need some room on this guy. Okay, so I'm scrolling down. I'll go over and back, and all my stuff will be here. Okay, so this is where we're at. Now we're going to use our properties of sigma, 1/2. Actually, I'm going to do my squaring first. From 1 to 6 of 16 minus, well, 4 is 16. 4 minus 1/2 is 2i, and I want to have another 4 minus 1/2, so I have 4i plus 1/2 I squared is 1/4 I squared. Of course, combine like terms. We're still going from 1 to 6. 16 minus 16 is gone. Minus a negative is plus 4i minus 1/4 I squared. And now is when we get to our rules for sigma notation. 4i, that's 4 times the integers. The integers, remember, are n times n plus 1 over 2. Right, so I'm going to write down on the side here for those who forget. I going from 1 to n of I is n times n plus 1 over 2. My n didn't work out there. While we're at it, we're going to need the I squared formula as well. That is n times n plus 1 times 2n plus 1, all divided by 6. Okay, so 4 times the integers. Well, n is 6 in this case, so it's 6 times 7 over 2, minus 1/4 times the sum of the squares. That's this formula. 6 times 7 times 13 divided by 6, and from here it is just algebraic. Check this out. 4 and 2 reduce. 6 and 6 cancel. So I have 1/2. Well, that's 42 times 2 is 84. This is 7 times 13, that's 91, divided by 4. So I have 42 minus 91 over 8, which is 42. 91 over 8 is 11 and 3/8. So we're at, what, 30 and 5/8 for our upper sums, right? That is an over approximation, upper sums, which for this particular problem was synonymous with our LRAM. There you go, an example of left rectangle approximation method, which gave us upper sums. I hope you enjoyed that video. Have a nice one.